Welcome guys, in this video we are starting our next big chapter on integration. At the very start of this course we mentioned the following two fundamental problems, tangent line problem and area problem. Those gave rise to a bunch of ideas in calculus, and up to this point we were working with differentiation. Now if we look at the area problem gave rise to the integration. And let's start with an overview of an area problem. So formula stated, area problem is given as follows: given a function f that is continuous and non-negative on interval from a to b, find the area between the graph of f and the interval on x-axis ab. So if we have the following graph, we would like to find an area below it and above x-axis. So there are two fundamental approaches. First one is logically straightforward. We can split our area under the curve into the following rectangles, and intuitively, if we separate that interval from a to b into n subintervals, and then if we approximate this area under the graph as a sum of the following areas of rectangles, as we increase n up to infinity, we see that our approximation will get better and better, and this area under this graph is equal to the following limit of the following sums of these rectangles. Although this method is very intuitive and makes logical sense, in some cases calculating this integral might be troublesome. In the late 19th century, Newton and Leibniz separately derived the following interesting property. They found that if function ax here denotes an area under our curve f of x, starting from point A and running up to some arbitrary point x, then if you take derivative of this function a of x, it is equal to this curve f of x, to this function that defines this curve f of x. And then if we would like to find this area under the graph, what we need to do, we need to find an antiderivative of this function a prime of x, or antiderivative of function f of x. And in this chapter, in chapter 5 on integration, we'll take a look at both of these approaches. In later sections, we'll work with Riemann sums, and we'll calculate areas under curves using the following rectangle method, and we'll calculate these limits, and we'll also be working with antiderivatives and integrals. So we mentioned antiderivatives previously. Now let's define what do we mean exactly by antiderivatives. A function big F is called an antiderivative of function f on a given open interval if derivative of big f of x is equal to small f of x for all x in the interval. So for instance, big f of x that is equal to 1 over 2x squared is an antiderivative of f of x is equal to x, since if you take derivative of big f of x, it is equal to 1 over 2 multiplied by 2x, so it is equal to x equal to f of x. Now, however, you can also obtain other antiderivatives. Let's call this as big G of x by, if you found one particular antiderivative, then you can find all other antiderivatives by adding some constant to it. Then 1 over 2x squared plus some constant will be a general form of antiderivative for a function f of x equal to x. And for instance, you can find, if you found one particular antiderivative, let's say 1 over 2x squared, then you can find others by adding constants. So for instance, 1 over 2x squared plus 2 plus 5 and so on. All these are going to be antiderivatives of your function x. Now question is there any antiderivative that cannot be obtained by simply adding a constant to one of the known antiderivatives? And the answer to that question is no. And these findings are summarized in the following theorem. If big f of x is an antiderivative of small f of x on an open interval, then for any constant c, the function big f of x plus c is also an antiderivative on that interval. Moreover, each antiderivative of f of x on the interval can be expressed in the form big f of x plus constant by choosing the constant c appropriately. Now, taking derivative of antiderivative of function f of x, we'll get to the function f of x back. We can rewrite this equation using integral sign as follows here. So integral of function f of x is equal to antiderivative of f of x plus constant of integration. This constant here is known as constant of integration, and this sign reads as indefinite integral. We call it indefinite since the result here is defined by a family of curves and is defined only up to constant. You guys are probably familiar with the definite integral sign where we have lower and upper boundaries in our integral sign. We'll consider this topic a bit later in this course. So if we find one antiderivative of function of f of x, then we can find others by translating this one antiderivative by vertical y-axis. These are known as integral curves. So taking derivative of integral of f of x, we'll get back to f of x again. The process of integration is, the very basis of it is essentially making an adequate guess. There are some techniques that will help us to make that guess. However, if you look at the general picture, it's just making a guess. Many basic integration formulas can be obtained by looking at an appropriate differentiation formula. For instance, if we are looking at an integral of 1 dx, then we know that derivative of x is equal to 1, so integral of 1 is equal to x plus constant c, and so on. For instance, we know that derivative of sine of x is equal to cosine of x, meaning that if we are looking for integral of cosine of x, then it is equal to sine of x plus constant. There are some properties of indefinite integral similar to the properties of derivatives. So if we are integrating some constant multiplied by function f of x, then we can factor out the constant. And we can, if we are looking at integral of a sum of two functions, then we can calculate integrals of f of x and g of x in this case separately, and then just sum up their antiderivatives. And similar case for difference of integral of two functions. So these properties can be nicely summarized in the following example here. Let's assume that we are trying to integrate the following polynomial here. Then we can find the integrals of this separately. We can factor out 3, then find the integral of x to the power of 6, which is equal to x to the power of 7 over 7. So then we are going to separately find integral of second term here, minus 2, integral of x squared, which is x cubed over 3, and so on.